Do you introduce me?
I think it's all I think recording.
Oh, I don't.
It's recording.
Okay. Right.
Okay, so I think we should get started. Thanks all for coming for the first IMA data science seminar of this semester. Today we're happy to have Frank, who is a PhD student in the math department. He's going to talk about inference learning of solution operators who are linear infinite PDEs.
Okay. Thanks for having me this afternoon. So first, this is a collaborative work with Yulong, Riley, and Tianhao. So it's an all UMN team for this project. So most of the content of this talk is motivated by development in foundation models, which loosely speaking are these large deep learning models that are pre-trained on really large amounts of diverse data, and then they're adapted to solve a variety of downstream tasks during inference. So I think the most popular examples of foundation models are large language models like ChatGPT from OpenAI. Other big tech companies have their own LLMs. So, these you can ask to do pretty much anything. Like if I wanted to ask it for an introduction for this talk, I could do that. And the consequence of their expressiveness is they have to be trained on a really large amounts of data. Maybe less popular, but a burgeoning area of application is using foundation models to solve domain-specific problems in science, like partial differential equations. So this is a recent work by Stanley Osher and his postdoc about in-context learning of PDEs. They developed this pretty complicated architecture that is basically a foundation model to solve a variety of partial differential equations. There's another work at NeurIPS last year that develops scientific foundation models. So those experimental developments are largely the motivation of this work. So if you have a pre-trained foundation model and you want to use it to solve some downstream task at test time, then you have to give it some information associated to the new task. And there are various ways of doing this, two popular methods being either fine-tuning or in-context learning. Fine-tuning involves actually updating the weights of the pre-trained model given some demonstrations of or data from the downstream task. So there's this diagram. So you do pre-training on a very large data set, and then to solve some downstream task, maybe you have some smaller amount of data for the downstream task. You can update the parameters by building some loss function from the data according to the downstream task. The other method called in-context learning, it basically primes the foundation model by conditioning on a prompt corresponding to a few labeled examples from the downstream task. So this is an example. If you're asking a pre-trained model to do translation between English and French, so you give it a few labeled demonstrations, and then at the query point, you hope that it predicts the right word. So in this case, we want it to predict fromage for cheese. And I think a benefit of the in-context learning is that you make prediction on the downstream tasks without updating the weights. So that's a very attractive feature of these foundation models, is the pre-training may be very expensive, but once they're trained, you can ask them to solve a variety of tasks without any parameter updates. And so that was sort of a perspective from NLP. A more mathematical framework is to describe a task you want to solve as a function. And in this case, an in-context learning model will take as an input a prompt just consisting of some labeled examples corresponding to the tasks and a query point that you want to find the label for, and the output of the in-context learning model hopefully corresponds to the label of the query point. So what does this task F represent? So in NLP, the task is modeling the underlying question and answer pairs. So for machine translation on the previous slide, maybe there's some function that describes the map from the English word to the corresponding translation and French. In the applications to science, maybe the task is an operator that describes the dependence of the solution on the various parameters of an equation. And I think the most important thing to highlight here is that in-context learning is very different from classical supervised learning. Maybe one way to think about this is you can think of the in-context learning model as sort of solving a supervised learning problem at inference. So the data of the input to the in-context learning model itself defines a supervised learning problem because you have these labels corresponding to the downstream task. So it's sort of crucial during pre-training that you have, a wide variety of these prompts. So I guess one way to think about it is the in-context learning model has to identify the function f, or the task, from the labeled examples, and then use that information to predict the label of the query. So it's learning to learn in some sense.
It's helped to add more data in context learning, or is there a point where making n larger doesn't help?
That's a good question. I think people have usually observed for the length of the prompt, it's helpful to increase it. But in a lot of the applications, it's still pretty small. So you're not really seeing the asymptotic behavior. Like in the in-context operator network by the Stanley Osher's group, I think in their experiments, they have like 5 labeled examples at inference time. So it's not clear if you increase that, what the asymptotic behavior would be.
What's the difference between the pre-training and the training for the in-context learning?
I guess pre-training is sort of called training in this case. It's just to say that in other settings, if you do fine-tuning, then you may do some additional training with a much smaller amount of data, whereas pre-training, you have a very large data set. But in the in-context learning framework, the pre-training is the only training that's done because you don't actually update the parameters to perform inference. Any other questions on the setup? So some questions to keep in mind for theoretical analysis is, I guess, first is what kind of models can perform this in-context learning. I think that the most popular architecture is the transformer-based neural networks. Recently, state space models like Mamba have also shown the ability to do in-context learning. I think, before transformers, people used RNNs, recurrent-based neural networks, to do sequence modeling. And if an architecture can perform in-context learning, then how large does it need to be? How many parameters? How much data do you need is another question. And in this setting, the data can refer to 2 different things, either the number of tasks that you see in pre-training or the number of examples, labeled examples that you see for each task. And usually those are sort of on different orders of magnitude. I think the number of tasks might be very large, whereas the number of labeled examples per task may be on the order of 10 or 100. And maybe a third question is, how do these models perform on these tasks arising from problems in science and engineering, which are characterized by challenges such as high or infinite dimensional data arising due to the discretization of continuous problems, and also the tasks with very complex structure arising from PDEs and other physical phenomena. So as a test case, we consider an in-context learning problem defined by this family of linear elliptic PDEs. So the solution operator that maps the right-hand side f to the solution u is parameterized by these 2 functions, in this case, the diffusion coefficient a and a potential function v. I think the linear elliptic PDEs provide a good starting point for this analysis for a few reasons. That it's still broad enough to consider situations of physical interest. I think maybe most commonly these PDEs are used to describe like steady states of the heat equation or other parabolic equations. But they're also linear, which makes a lot of the analysis tractable. And then on the PDE side, you have the nice regularity theory. So our goal is to learn this map from F to U, the solution operator, in context, meaning over, various choices of the parameters of the PDE. And so this is an infinite dimensional problem, as it's stated. So to make it computationally tractable, you have to do some kind of spatial discretization. And I'll maybe talk more about how that's done in later results. But the point is that after discretization, this family of PDEs gives rise to a family of linear systems. And our goal is equivalently to learn the family of linear systems in an in-context fashion. So here, this D0 I'm using to denote the physical dimension. And this D, this lowercase d, is the dimension corresponding to the discretization. You can think of that corresponding to a mesh size. So the larger this lowercase d is, then the closer you are to recovering the continuous dynamics. So how do we prepare the data in this setting? So it's common to define a single matrix denoted here by Z that includes both the labeled examples and the query point that you want to perform inference on. So into a single matrix. So here the Fs are these discretizations of the source terms or the right-hand side of the PDE, and the U is the corresponding solution to the linear system. And this 0 in the bottom right corner is really just a placeholder for the labels that you're trying to predict. And so then when you want to perform inference, you get a new prompt corresponding to a new matrix A coming from a different PDE, and you want to predict the unknown label. And so we have some statistical assumptions on how the structure of the matrices A and the right-hand side vectors F. So they're described by some underlying probability distributions. We'll put more assumptions on those when we state the main results.
So that should be ZI, right? Not ZJ.
Yeah, sorry, ZI. Yeah. Yeah, I guess there's no J here. I've just confused my indices a bit. But yeah, so there are different indices. Here, I guess the I is indexing the task. And then yeah, J, I guess, is indexing the labels for the task. So it gets a little bit confusing. So at this point, we haven't really talked about the model, sort of how we're going to do in context learning. The most popular architecture is a transformer, and transformer-based neural networks are distinguished from other architectures like MLP layers by this self-attention mechanism. So attention, it basically defines a map between sequences. You give it a length n sequence, attention returns another length n sequence, and it does some non-local operation. So there's some way of aggregating all the tokens in the sequence to return a new sequence. In this case, if you think of Z as the prompt matrix with the structure described on the previous slide, then a self-attention block has the following structure. So there's a residual connection, and it's parameterized by these three learnable matrices, P, K, and Q. And there's a nonlinearity given by the softmax function, which is just you have a sequence, maybe X is X1 to Xn, then the softmax of X is another sequence of length n, and the jth entry will be e to the x j over sum over I to the xi. And for the matrix, I believe it's applied column-wise in this case. So yeah, the softmax, it originates from the use of attention in these machine translation problems where you're sort of trying to output this probability distribution over what the most likely word over vocabulary is after conditioning on the first few words of a sentence. And something to note is that these learnable parameters, P, K, and Q, their dimension D or 2D depends on the spatial discretization of the PDE, but not on the sequence length. So this allows attention to operate on sequences of arbitrary length. In particular, you can have sequences of different lengths for each training example, and you can have a different number of labels in pre-training versus at inference. Yeah, so the I is indexing the task. It's basically indexing which PDE you're solving. There's not there's basically no index of discretization in this slide. It's yeah, this is all after we've done some like Galarkin method or projection onto finite dimensions.
The assumption that your AI and FI are subject to some distributions. That's the reason that you don't need to retrain them.
No, I don't think that's the reason that we need to do retraining, because even
You're saying that once you train, then you can fit in whatever prompt you want.
yeah, that's true.
Because prompt is also
Oh, we also consider the case when maybe the distributions at inference are different than the distributions at training. And in some cases, the transformer will be robust in those cases. So so it is learning some part of the distribution, but I would say that's not the main reason why it's able to do in-context learning. One thing I forgot to mention is this M, which is not a learnable parameter. It's referred to as a masking matrix, and it's the basic reason why you have it is you like the output of this transformer to be some function maybe of the query point that's conditioned on the first n labels, and this masking matrix is basically just ensuring that you're not also conditioning on the point that you're trying to perform inference on. So this is it's related to this asymmetric structure of the prompt matrix. And so some more on the model. So I guess if you remember that this prompt matrix has a placeholder for the label of the query point. So that's basically going to be our output. Even though the attention defines a mapping between whole sequences, we really only care about these last D rows of the last column of this prompt matrix after applying the model. So that's what I mean. We take a single attention layer, we extract the last D rows of the last column, and to simplify assumptions, we omit the softmax linearity, and we merge some of the parameter matrices. So this architecture is sometimes called a linear attention layer, which is a little bit misleading because it's not linear as a function of the prompt, and it's also not linear as a function of the parameters. It's really just to say that you're dropping the nonlinear activation. Yes.
Where's the theta in the model?
Oh, I guess the theta here is basically the P tilde and the Q tilde. So those are the two learnable matrices in this case. And we make some additional assumptions, which are kind of justified by the fact that you don't need all of the blocks in these matrices if you're only reading out the last D rows of the last column. So this motivates a certain structure of the attention matrices. So the P and Q are going to be D by D matrices. Those are the two learnable parameters. And then you can show under this parameterization that the output of the transformer is explicitly given by this equation. So we have the matrix P times the A inverse, where A is the matrix describing the downstream task. times this Fn, which is like an empirical covariance matrix of the source terms, and then times the parameter Q applied to the query. So this is basically what our version of the transformer is doing at inference.
You miss out on much by getting rid of the softmax.
That's a good question. I think in these settings, when you're doing like linear problems, linear regression, or solving linear systems, I don't think you miss out on much. And in fact, I've seen some papers suggest that actually using softmax can limit the performance because there's some kind of strong inductive bias of assuming that the entries are all normalized. But for nonlinear problems, it's a good question. I don't know. I think from a theoretical perspective, it can be kind of difficult to use the softmax when you're trying to make explicit constructions because it's so non-local. So I've seen some papers use nonlinear attention for nonlinear problems, but they assume instead of doing the softmax that you just apply some kind of pointwise nonlinearity, like in an MLP. And in that case, I don't know if you're losing anything in practice from omitting the softmax, but it's a very good question. Yes.
So does the sequence of the prompt matter in the training?
In our case, no, not really. Because you can see that the output, it only really depends on this covariance of the source terms. So for time-dependent problems, if your sequence, your prompt corresponds to like a trajectory of some time-dependent system, then you need to do you need to sort of encode the positions of each label in the prompt matrix. But in this case, it's not so important. So that the role of each column is basically symmetric. It's just a couple more remarks on the training and the generalization. So for training, we have this empirical risk function. So it's indexed by the capital N, which is the number of tasks, and the lowercase n, which is the number of labels for each task. And so I mentioned you can, in theory or in practice, use different numbers of labels for each prompt. But for the theory, we're just going to assume that in training, the number of labels per prompt is fixed at lowercase n. And then this theta, indexed by the two n's, is the empirical risk minimizer. And then to measure the performance of the pre-trained transformer on new tasks, we use a population risk function, which is sort of obtained from the empirical risk by taking the limit of the tasks to infinity and also changing the length of the prompt. So I think it's practical to consider at least two different prompt lengths between training and inference, because during training, you may be training on synthetic tasks where you can actually prepare more labels, whereas in practice, if you're trying to solve some task at inference, you probably can't actually prepare so many labels. So you may just have a smaller number of labels from data collection or something. And so our goal is then basically, what is the prediction error measured by this population risk of the pre-trained transformer from empirical risk minimization. And I'll just say one thing we're not really considering is the training dynamics. That's something that's been considered in other works. Our focus is more on the statistical error and effects of possibly shifting the distributions. So I'll first talk about the case where you just have one distribution for the tasks and one for the source terms. And after that, I'll talk about what happens under shifts. So we need some assumptions for the theory, and I think they're pretty mild. So for the task matrices, we just assume that they're symmetric and uniformly positive definite, in the sense that you have these upper bounds on the norms of the task matrix A and the inverse of A that hold uniformly. I think some kind of bounds on enough moments would be sufficient for most of our arguments, but it's just simpler to assume these uniform bounds. And for the covariates, the right-hand sides, we just assume that they're Gaussian with some covariance. And I'd say these assumptions are mild in the sense that, at least for the matrices, they respect the assumptions that the tasks are discretizations of these elliptic PDEs. So you have the symmetry and the upper and lower bounds. So the first result is about I call it in-domain generalization, because we're using the same distribution on A and F that we use in training and in inference. And there's this result that under the additional assumption that the m is less than or equal to little n, then you have this high probability bound on the prediction error in terms of each of the sample sizes. And so I kind of like to group the two terms in this way, where you have the first term that's, I like to call it in context generalization error, that corresponds to the length of the prompts. And that's sort of corresponding to after you've done pre-training, your transformer is behaving like a supervised learning algorithm, and the sample size then depends on the number of examples. And then you have this other source of error that's the pre-training generalization error, which depends on how many tasks do you need to actually train your transformer. So one thing to notice is that at least for the in-context generalization error, you have these two different rates, one for the context length during training, which is the lowercase n, and one for the context length at inference, which is the lowercase m. So they actually appear to play different roles in the error. And we're not the first to observe this in theory. And the rate for the capital N, we conjecture may not be sharp because of the techniques we've used, but we also do some numerical experiments to try to verify these scaling laws. And actually the 1 over square root of capital N, we appear to see in the numerics as well. And let's just say something quick about this assumption that the little m is less than little n. In the regime where n is greater than m, we have an additional error term that's corresponding to the mismatch between the lengths of the prompts. And so the dominant term will be 1 over little n in that case. But I'm pretty sure that this is a proof artifact, just because we don't see this in the numerics, even though we consider regimes in the numerics when little n is less than m. Yes. Mm-hmm. Mm-hmm. No, I'd say the d, the lowercase d is related to how you discretize. So maybe you have some. Actually, I think the next slide will explain this. But so basically you have some basis for H1 space. Maybe you truncate the basis up to the first d functions, and then you consider the associated linear system from the PDE after basically projecting all of the coefficients onto this basis.
You discretize it in certain ways, and you train you train the operator.
Mm-hmm.
Then you input binary source. Then you want to output a binary solution. Is this error how you what's accuracy?
Yeah, that's a great question. Actually, under our framework right now, that such an experiment isn't permitted because the dimension of the parameters of the transformer actually depend on this resolution, the number of basis functions that you use in training. So it does require that you use the same scale at inference. I think we explored maybe one experiment where maybe we used like a Galerkin discretization during training, and then at inference we use like finite difference instead, but with the same number of grid points, so that we could still use the same parameters that we pre-trained. In that setting, it's really hard to say what's going on, but I think that's an interesting question to try to maybe redefine the model in a way that can, be used to solve equations at different scales.
That's sort of why we dimension subject.
Right, yeah, I mean, yeah, I sort of thinking that, I don't know, like, for example, there should be some classical discretization error here in your estimate.
Oh, yes. Okay, so that will come up in the next result. I think the reason why you don't see anything for discretization error in this first result is it's really just the error in learning the coefficients for the PDE. You've sort of forgotten the PDE structure and you're trying to recover the linear system. The next result is about learning the PDE. And so in this case, you have this result that says that you have the mean squared H1 error between the true solution and the function obtained from the pre-trained transformer. And you have basically a sum of these two terms, or the first term is a classical discretization error. So the bold U is basically the vectorized or discretized version of U after you basically clip, a certain number of the coefficients. And the non-bold U is the true solution. So this first term really only depends on the choice of discretization. The second term is basically the same term from the previous slide. It's the statistical error of learning the linear system with the caveat that you have this constant CD. This is basically measuring, if you're matching the coefficients of the linear system, what does that tell you about the H1 norm? The answer is, of course, as you increase the number of coefficients, it's going to tell you less and less because you're adding these higher frequency terms. So this indicates there's some trade-off between the dimension of the discretization, which I'm sure we're not the first person to observe this. Even before in context learning, you do pins or deep RITs, maybe you see something like this. So that the first term will be too large if the number of coefficients is small, because you're not really capturing the high frequency components of the solution. The second term will be large because you're learning a linear system with more components, so you need more examples in that case. And if you're using the H1 norm as your metric, then it's going to be even larger. So we'll come back to this when we do some numerics. But there is definitely a trade-off in terms of how you choose this D. Yeah, CD scales with D, yes. It's probably like D squared, I think. Any other questions to this point? Okay, so I'm going to talk about out of domain generalization. So this is where maybe I change the metric that we're using for prediction. The way I change it is I take the expectation over the distribution on the matrices A that's different from the distribution during training. So maybe an example is if you solve some equations during training, maybe minus Laplacian plus VU equals F, and you have some distribution on the potential V, and then maybe at inference you solve a equation with a non-constant diffusion coefficient. So changing the one or more of the parameters of the PDE from constant to non-constant functions is an example of such a distribution shift. And so the goal is now to bound the distribution, the population risk after distribution shift, but where the pre-trained transformers were trained basically using the old distribution. So for this, it's useful to define these what I call infinite length or infinite context population risks. It's basically obtained from taking the population risk and taking the limit as m goes to infinity. Maybe I refresh you. Yeah, so you remember this, we have this explicit output of the transformer in terms of this empirical covariance of the source terms, F. If we assume that there's some, population covariance matrix that describes the distribution, then you can get some kind of context independent generalization of this risk just by replacing the empirical covariance with the population covariance. So that's what we do here. And so we use this to give a pretty abstract looking theorem that quantifies the prediction error under task shifts. So you have these 4 terms I've really grouped into 3 different categories. And I'll go through maybe term by term to say, how you expect them to behave. So the first term is this in-domain risk. We know from the first result I showed that there are some, you can bound the in-domain risk in terms of each of the relevant sample sizes. So you'd expect that to decay as each parameter describing the data is large enough. I think the interesting thing about this bound, I think the most exciting part is the second term, which is quantifying the error explicitly incurred due to the distribution shift. It's of the form, some discrepancy between the pre-training and downstream task distributions divided by the prompt length M at test time. So the distribution shift error is going to be order 1 over M, even if the distribution shift itself is order 1. I think so that's maybe highlighting the ability of these transformers to adapt to downstream tasks. And then you have these 2 abstract looking terms in terms of so the first term is the distance between the empirical risk minimizer and the set of minimizers of this infinite context risk. So you expect to have some kind of continuity in the sense that the empirical risk is converging to the infinite context risk, as I guess both N and capital N tend to infinity. So you can show that you have convergence of minimizers, at least qualitatively, with high probability. The only term that we haven't accounted for is the final term, because this M prime is the set of minimizers of the infinite length population risk corresponding to the downstream task distribution. And this theta of N and capital N is an empirical risk minimizer trained on the pre-training task distribution. So it's not clear that you can expect that term to vanish without further assumptions on 1 or more of the distributions. And so this leads to a notion of task diversity. I think it's a simple observation that if you assume that the set of minimizers corresponding to the pre-training distribution is contained in the set of minimizers for the downstream task distribution, then you can basically absorb the last term into the third term, and you get a bound where all terms are expected to decay with the sample size. And so this property, this assumption that you have this inclusion of sets of minimizers, it looks kind of abstract, but you'll notice it doesn't depend on the data. It only depends on the 2 distributions that you're considering. So you can sort of take this as a definition of diversity of the 2 distributions. So we say that the pre-training task distribution is diverse relative to this downstream task distribution if you have an inclusion of sets of minimizers. It looks, pretty abstract. We have some examples for when this diversity condition holds. The very simple example is just if you have inclusion of the supports, then you have a diversity. So if the downstream task distribution is supported in the support of the pre-training task distribution, then diversity holds. And so because we're doing linear attention, this diversity condition is actually fairly tractable in terms of linear algebra, and it's really corresponding to an inclusion of centralizers for the sets of matrices which commute with all the matrices in the support of the task distribution. So there's this one condition that says if the support of the pre-training task distribution has a trivial centralizer, meaning that any matrix P commuting with all tasks has to be a scalar, then you have this absolute diversity in the sense that the PA will be diverse basically no matter how far you shift the distribution at inference. So that seems pretty powerful, and it matches with some empirical studies that have suggested like a threshold or a phase transition for out of distribution generalization in terms of the number of tasks. There is a failure case to consider that if the support of the pre-training task distribution is a set of matrices which are all diagonal in some common basis, then in general, it will not be diverse for the downstream task distribution. The reason or the intuition is that there are some minimizers of this infinite length population risk, which will memorize the common diagonalization and thus not generalize. So it's a bit abstract, but there are some sufficient conditions that can ensure this task diversity. And one last theoretical result is about distribution shift on the covariates or the source terms of the PDEs. So in this case, we consider the shifts of, Gaussian distributions where you modify the covariance. And in this case, you don't get as nice of a result. You still get that the out-of-domain generalization is bounded by the in-domain generalization and some metric corresponding to the shift in distributions. I think those maybe should be squares. But in this case, you see that the error from the shifting the distributions, it can't be reduced just by increasing the length of the prompt. You have this second term that's like an absolute factor. And I think the reason is pretty intuitive, that the attention parameters are learning to adapt to the covariance of the source terms. So we're also not the first to observe this, that generally the transformers are more robust to tasks than to task shifts than to covariate shifts. Maybe so I'll talk about some numerical results now. The first numerical result is verifying the neural scaling laws, or how the prediction error in the in-domain generalization setting scales as a function of the sample sizes. So these plots A, B, and C are basically plotting the error in log scale with respect to each of the relevant samples. And so the slope is basically going to give you the exponent in the scaling law. And in this case, we do see that we have the approximate slopes of what's it, 1 over m plus 1 over n squared plus 1 over capital N to the 1/2. So the experiments validate each of those exponents. And it also suggests that maybe this holds not just in the region where the m is less than lowercase n, but in general. The last plot, D, is just plotting the L2 coefficient error for learning the linear system as a function of the dimension. And it's not surprising that you generally need more examples to learn the linear system if you have a larger dimension. So the second experiment is on the PDE recovery error. So the plot on the left, plot A, is comparing the transformer solution with the true solution, basically obtained by doing Galerkin method with a lot of basis functions. And you can see here there's still some error. I think the main reason why there's still some L2 error between the purple curve and the green curve is just maybe the sample size isn't large enough. I think that's maybe one challenge of this project is the scale is quite large because you have the number of tasks n, and then you also have this data that's very high dimensional because you have the d, the number of coefficients, and n, the number of demonstrations, and both of those have to be large enough to get a small error. But you can still see, even in this low data regime, that the green curve is adapting to the sort of shape or derivative of the purple curve. You see this orange curve is the transformer with a very small number of basis functions. You can see that that curve is not really learning any of the shape of the true solution. The plot on the right is the H1 error for learning the PDE with respect to the number of coefficients that you use. So you see this trade-off that I described earlier in this U-shaped curve. So when the number of basis functions is too small, the discretization error dominates. When the number of basis functions is too large, the statistical error dominates.
Did the optimal D change much when we ran this on different PDEs? Was it usually kind of in that sort of lower area?
Yeah, that's a good question. We didn't check what the optimal D was for every coefficient, but it would probably depend on how smooth the coefficients are. So if you, depending on how strong the high frequency components of the true solution is, that's going to determine where the optimal D is. So another experiment is on the task distribution shifts. So this is one example where we're solving this PDE, and we change the distribution of the coefficients between training and testing. So here, we're shifting the distribution of the diffusion coefficient A, and these parameters, alpha and tau, that are being plotted, these basically determine or parameterize the distribution of A. So to write A, we basically write it as a log normal distribution, where the log of A is a normal distribution sampled from some covariance operator, minus Laplacian plus tau times the identity, some power minus alpha. So this alpha is determining the smoothness of the random field. So larger alpha will mean weaker high frequency components. And so during training, we use, I think alpha is 3 and tau is fixed at 5. And then at inference, we vary the alpha between 4, 2, and 1. And we see the relative error is basically the same for each of the choices of alpha, it's kind of validating that these transformers are pretty adaptive to task shifts. I would say it's telling that the transformer is even able to adapt to the case where the distribution of the coefficients is less smooth at inference compared to training. I think it would be not so surprising to see the transformer perform well on smoother PDEs. So the second plot is a distribution shift on the potential function V, which is parameterized as a piecewise constant, where each of the constant values is a uniform in some range. And so we shift the distribution of V by shifting the range of the uniform distribution. And in this case, you do see some more extreme, you see more pronounced changes in the loss incurred by this distribution shift, but you still see the decay with respect to the prompt length, which was shown in our result. I think this is the last example. Maybe there's one more, but this example I think is very interesting. We wanted to do some experiment to test this task diversity condition. So we considered basically pre-training the transformer to solve a PDE with constant coefficients. So you parameterize the coefficients as constants, but you vary the constants among the tasks. And this is the reason why you expect this distribution not to be diverse, is because the the PDE operator in that case is given by maybe some constant times Laplacian plus another constant times the identity, maybe inverse, and this diagonalization doesn't depend on the values of the constant. So this is an example arising from the PDEs where the task distribution consists of matrices diagonal in a common basis. And then at inference, we consider testing the performance of this transformer on non-constant potentials, namely where we make the V a piecewise constant, as in the previous slide. And so the two plots show basically the same experiment, but with two different initialization schemes for the transformer. The first initialization scheme is initializing the attention matrices around the identity matrices. In this case, we sort of expect, I mentioned that the cases where you won't generalize out of distribution are where the P and Q memorize the common diagonalization of the task distribution. So you think the identity should work because it commutes with all matrices. The plot on the right is initializing the parameters randomly. And what you see is basically comparable test loss when the coefficients are still constant, but a great difference when the coefficients are non-constant. I think the last one is covariate shifts, which is not so interesting. It's known that these covariate shifts, the transformers are not going to be robust under these. So we consider basically one shift on the left where you just scale the covariance matrix by a fixed multiple, and an example on the right where you shift the parameters of the covariance, which basically the same parameters as in this slide, these tau and alphas. So shifting the smoothness of the covariance. And in either case, you see that the transformer is very brittle under these distribution shifts. So I'll just briefly comment on the basically future directions to go from here. I think that the main direction is try to generalize these to either nonlinear PDEs, where the solution operator is not linear, or to at least time-dependent PDEs, where the prompt is corresponding to a whole trajectory rather than just independent shots. In this case, it's natural to ask if there's some role of using a nonlinear activation in the attention or using multiple attention heads. I think maybe another question is just to verify these task diversity conditions for the distributions corresponding to PDEs. I think that the numerical experiments suggest that there is task diversity for these distributions, but we weren't able to prove that. And maybe the last question is just the scalability and application to high dimensional problems, because we know maybe using the Galerkin method to discretize, it may not be the most effective way to do these higher dimensional problems. And right now it's, even for 1 or 2 dimensional problems, it's still quite expensive to perform these simulations. I think that's everything. So thank you for listening.
Time for questions.
So back to the generalization error, for the pages 2000. Can you comment on what's the difference compared to other model, like maybe neural network or maybe like the open source reflection? Is there any gain or?
That's a good question. Yeah, I think fundamentally we're kind of considering different problems than like supervised learning. So I mean, it's not clear if these other models that you mentioned could perform in context learning. I think there has to be some kind of non-local mechanism that uses all of the tokens in the prompt. But I think the 1 over m is sort of the rate corresponding to just learning the downstream PDE. I think, maybe the second term, the pre-training generalization error, is maybe more specific to to the transformers.
Yeah. So, yeah, it makes it a lot more clear. So I guess why you want to make it linear, so you just make it like that, you know, the x is equal to b.
Mhm.
So why does it have to be vertical? So, is that come up? Versus hyperbolic?
It maybe time independent was the most important thing, that it was just an IID problem.
Yeah.
Whereas if you made it, you know, I guess if you could probably do the same thing for like parabolic or hyperbolic equations if you were learning like the map from U0 to UT, but if you wanted to learn a trajectory.
Like what are the two x minus two y y? Hyperbolic, like it's going. So it's still linear, it's still right as a linear system, like this was how it's trying to do. Is the analysis apply there? Does it have to be elliptic?
I think for learning the discretized version of the problem, I think the same analysis would hold up. You might see differences for the PDE error when you consider discretization, but I think if it's still linear, yeah, I think the same argument works for turning it into a linear system and learning that linear system in context.
Or like positive.
I think the analysis will be some PST, right? Ace PST matrix. It's probably that.
Yeah, that's true. I mean, yeah, maybe for the analysis to go through, you may need some upper and lower bounds on the matrix A. But for experiments, I don't know.
Yeah, we haven't done experiments for like high for manipulation.
Yeah.
Does it use the fact that it's linear in some crucial way as well, or can this extend to novel?
I think linearity is crucial for the task shift. With the equal generation, I think that you can prove the same for much larger class of PDEs. The task shift, I think it's much better.
Why does the task shift?
It's very hard to characterize the along the problem. More questions?
That's a good question.
Maybe spaceless model. That's for
Questions like, so in general, yeah, just forgetting that I didn't answer this before, like, in general, can people put the lower bound in the generalization?
In general, for supervised learning, yeah, you can generally prove lower bounds in terms of the function class you're trying to learn. Like if you're learning like a Lipschitz function in high dimensions, then the sample complexity is like 1 over n to the 1 over d, and that's generally optimal in the sense that you have another lower bound. For in-context learning, it's a good question because you consider the lower bounds for each of these two terms separately. I think there's one paper that does this. They actually consider these minimax lower bounds for in-context learning, both for in-context generalization error and pre-training generalization error, but I haven't read their paper in depth. I think they're probably the only person to do that for this in-context learning setting.
Any more questions? Hey, maybe I can ask any questions from people on Zoom? No. If you know, that's thank you. Thanks all for joining. Meet next week.